Hey everybody, it's Josh Eisenberg. I was an OSDC-PIRE 2013 fellow this year. I was doing research at the University of Edinburgh Informatics Forum with Rosa Filgueira and Malcolm Atkinson, and I also worked with Andrew Bell from rock physics and geophysics. I wrote and I worked with RockPi. RockPi is a Python library for rock physicists. RockPi works in conjunction with the EFFORT database. EFFORT stands for Exploring Failure Forecasting in Real Time, and EFFORT is a scientific gateway that enables rock physicists to share data and the methods that they use to analyze their experiments. So the thing about RockPi is that RockPi allows you to access this database in EFFORT that has all kinds of different experiments. Some of the experiments include different volcanoes, like Hero and Etna. Some of them are lab-based experiments that explore brittle rock failure with acoustic emissions, and some of the data is synthetic data that's made to simulate all these different interactions that are going on with the rocks. So before RockPi, there was no standard way for the rock physicists to actually access this data and to process it. RockPi enables the scientists to get into the EFFORT database, pull their data, analyze it, model it, and plot it. And by using 4 different sets of functions, the rock physicists don't have to worry about as many of the computer science issues as they did in the past. See, they're rock physicists. They're not computer science PhDs. They shouldn't have to worry about all the coding problems that us data scientists do. The main goal with RockPi was to create an efficient language that would allow the rock physicists to just not have to think about the computer science aspect and to be able to easily communicate with the EFFORT database and get data and plots and figures that they could use in journals so they could keep doing their rock physics and progress their field. Alright. This frame shows a read operation. This is the first of the 4 types of operation. The command that the user enters is read rock data, and then with the parameter as ID rock. So ID rock is just the experiment ID in the EFFORT database. So when they run this function, RockPi returns a rock data structure, and you should be able to see it at the bottom, but it's not showing up for some reason. Alright, now this image shows the structure of rock data. Rock data is kind of, it's the smallest grain of information that the rock physicists actually use. So the read function returns the rock data structure. The rock data structure encapsulates everything that has to do with a particular experiment. The rock physicist never actually looks into the rock data structure. Instead, it uses the rock data structure as the input into the analyze functions and model and plot functions. That way it kind of puts a layer in between the rock physicist and the actual data. The rock data structure contains the repository data matrix, which is the actual stress and strain values or whatever things we're measuring in the experiment. The experimental metadata tells us information about the experiment that helps us run programs on it, and the operation log tells us the history of the particular rock data structure that we're talking about. The cool part about the rock data structure is that it allows RockPi to have a modular operation nature, in that the rock data structure is passed around from function to function, and that means you could define workflows, and you only have to input the rock data structure once, and you get different analyzings and different models and plots out of it, but only using one workflow. This is the analyze function. The analyze function edits the data that's in the repository data matrix. So let's say you want to smooth the data over or remove an outlier from the data. Then you input your rock data structure into the analyze function. RockPi does its work, and RockPi returns your rock data structure. And your rock data structure has an updated repository data matrix that's either smooth or the outliers are removed or whatever operation you want. And it also updates the op log so you know what you did in the future. So you're not wondering, what did I do to this data? How did I get here? So it allows you to reproduce your results. The third operation is the model operation. Model operations take as input the rock data structure, and it outputs a model file. The model file contains the parameters for a mathematical equation that actually explains the data, and it also contains statistics regarding the correctness of this fit. And it also updates the op log within the rock data structure, so you know what kind of model you did and where the model file is stored. The final type of operation is the plot operation. The plot operation takes as an input the rock data structure and the variables that you want to plot, and it outputs an actual plot, and it updates the op log to let you know what you plotted. You could also plot your model files from the plot functions too. Hello again. So those were the 4 functions, and those 4 functions can be used in conjunction. Like first you do the read operation to get the rock data, then you send it to the analyze function, and it does some correction based on the instrument, and then a different analyze function to do smoothing and to take out outliers. And then we want to model it to get an equation or 2 out of it and the statistics, and then we send it to the plotter to get images. So this process can be used many times. So let's say you want to do different time frames. So like you just do the same operation but over different time frames. So that's a way that you could use workflows with RockPi. And I want to thank you guys for listening. Sorry if I went over time. And and hopefully I see you guys all at some conference or at something in the future. And since my project was on RockPi, I'm going to leave you with some rock music.